All right, everyone. So today is Wednesday. Happy Thanksgiving. I would thought to try to make this lecture kind of shorter, but at the same time, I know I won't. And it's illegal for you to go home, so I might as well maybe use up more of your time to keep you infotained. I'm not going anywhere. It's going to be turkey with the cats. It's a real pain to try to get home and back again because, like, you know, when you have to be in class, well, anyway, you know what I'm talking about. You know now. Anyway, okay, so we're going to cover something today that's really awesome, and I use this all the time. This is the neatest thing I know, called the split operator. Split operator method. And heads up, I'm going to send you a very comprehensive textbook-like description of this because there's some nuances to here, especially the MATLAB programming, that I'm just not going to get across. So I'm going to give a big picture, and then we'll sit down in front of the computer, and I'm going to send you a PDF that describes this in very good detail with MATLAB scripts that you can cut and paste and watch. So anyway. So what is this? Oh, by the way, this is easier to make three-dimensional. I don't know if you noticed, but the finite difference, it's really hard not to do one-dimensional, or if you solve things in a radial sense, like we did with the particle and the sphere, that's kind of actually one-dimensional, isn't it? Three-dimensional is hard. Split operator does the same thing that the finite difference does, except it's way easier to do three-dimensional problems. And that's, you'd want to do that when you have like an asymmetric potential surface. So anyway, so I'll show you how to do this. And for your exam, I'll probably have you calculate everything with, I'll have you calculate particle in the sphere, like core shell quantum dot electronic structure with finite difference. And then you'll do the same thing with this and show that the answers are the same. But it mostly gives you some programming experience. And I'm telling you that, I mean, you know, it's more applicable in my group, but calculating the electronic structure of core shell quantum dots is something that you still see in papers all the time. So I'm able to give you something that's useful that you still see, that even today you see published. Okay, anyway, now how does this work? So what you're going to do is you're going to calculate the energy in the wave function given a Hamiltonian. Right? But of course, that's what quantum, I haven't told you anything, that's what quantum mechanics is. Okay, this is called a spectral method. It's called a spectral method because you're looking at the time evolution of the wave function. So here's, I'm going to show you how to evolve something in time. Now, we've actually already covered it, but I'm going to show you how to do it for real. Right? So you can make movies out of this, and you literally are going to be making movies. Okay, and so you need to use the time evolution operator. And so you know that looks like this. So a state evolved in time. Of course, this is a time-independent Hamiltonian. And we'll just keep things along the x-axis. I will show you how to do 3D some other time, or maybe on the computer, or maybe in a handout. Okay, now of course, the Hamiltonian is p squared over 2m. Of course, we'll make that an electron, so it's actually the number 1, like I covered last time, which for me was just a few minutes ago. Okay, of course, the potential is always based on position, and there you go. Okay. Now, one of the problems is, you know that momentum is, here, I want to show you some language that you hear frequently, but is never really described. Momentum is a non-local operator. You'll hear that a lot. What the hell does that mean? Think about finite difference. How did you calculate a derivative or a double derivative? You needed to know not only the wave function at the point you're trying to describe, but you need to know the value of the wave function forward and behind you. Non-local, right? So that's what that means. So a operator is non-local because to evaluate a derivative, you need to know what's in front and what's behind you using a stencil, right? A 3-point stencil. Okay, now that can be nightmarish. That can actually be incredibly difficult and to try to work with that numerically. So you know what I'd rather do? I'd rather drop this and treat the momentum operator like I treat the position operator, where it's equal, basically it's equal to itself, right? What's the position, x operator operating on a wave function? Well, you just integrate the wave function times x. I want to do that with p, and so there's no derivative. And you can do that because you did it on a homework. You just have to have the wave function in the form of the p wave function transformed to the p state, Fourier transform from the p state. And likewise, when you have x do its thing, you're going to have the wave function in the x state. So in the big picture, what you're going to do is you're going to take a state in position. We'll draw like a little Gaussian. Then you're going to do some operation in potential. Then you're going to Fourier transform it to p, do this operation, and Fourier transform it back to x. That's how you're going to do this. That's the big picture. And we're going to use MATLAB to do all the Fourier transforms. So that's actually a little tricky, which is largely what I'm going to cover. Okay, so again, we're not going to be using this operator because for various reasons it's actually like freaking impossible. But regardless, think of that homework where I had to calculate the average p for the wave function in p space, and it ended up being very trivial, right? It was just like x, except it's a different letter. Okay, now what I'm going to do is, now I have to think about, okay, here's the Hamiltonian. The Hamiltonian's composed of two terms. Now this ends up being a hell of a problem. Okay, so what I'm thinking of is I'm going to do this. Hopefully I'll just write this correctly. Okay, IT over h bar, that's right. P squared over 2. Minus, right? And then e to the minus IT over h bar v. Okay. So this is what I'm thinking. And it will operate on the state, the initial state, and it will start to move in time. Okay, now, again, this is in potential space. This is right in real space, x space. So this thing you can just do something with that. And the way you're going to do that is you can think of e to the I potential as like just cosine and sine of the value of the potential times t divided by h bar anyway. So seriously, cosine of the potential energy times some constants minus I sine of that times the wave function. It really is very simple. Okay, but then you've got this thing. And again, you don't want to be calculating derivatives. You don't want to work with the non-local potential. You want to work with the non-local operator. You want a local operator. So here's how you're going to do that. You're going to do e to the, you're going to write all this over again. So what you're going to do is you're going to use the fast Fourier transform algorithm in MATLAB. And okay, so anyway, so have this thing do its thing, Fourier transform it, and so of course you know that what that means is that really the state is then a function of p, and then you can do this operator. Now I know this is probably like kind of confusing. What does it mean? How does this work practically? Like, how do I put numbers in a calculator? This is probably still incredibly obscure how to do that. Of course, it's going to be easy, but give me a moment. Okay, now this is equation 1. Now the question is 1 correct? Again, I'll show you the tricky algorithms, and I'll show you how to make sure that you actually put in the numbers that are right. But here's the problem. Equation 1 itself is not correct. That sucks. So there's some consequences to that. Now let me explain why. Okay, why is one not correct? Okay, what I'm going to do is I'm going to call lambda as IT over h bar. Okay, call lambda that. And now I'm going to have operators A, operator B, which of course is momentum and kinetic energy. Let's not worry about that. I want to show you how it's expressed. What you want to know is, and I've already told you, lambda A plus B, is that equal to e to the lambda A, e to the lambda B? And the answer is no, it is not. Notice that's what I did. Right? When I went from here to here, I'm using this. I'm doing that. And it's not correct. Now, we're going to basically just do what I just described. We're going to do that anyway, to be blunt. But I'll show you the ins and outs of why that works. Okay, so now let me write out what the real equation is. You get an idea of how well, how meaningful is this. Okay, and this is, I'll give you the name out of respect to the people who did it. Baker, Campbell, House, Dorf. Oh, there's two F's. So this is the Baker-Campbell-Hausdorff formula, and it works like this. E to the lambda. Now, where this comes about is that these people were like matrix math people. But operators, more than ever, can be put into matrix form. So anyway, that's what they were thinking of when they did all this. Okay. So what does this equal? I mean, like really equal, because it doesn't really equal what I drew up there. This is what it really equals. E to the, let me put a little bracket, lambda A plus lambda B. Okay, if I stopped writing here, then we're set. There's no problem. But I'm not going to stop writing because unfortunately you run into this. You run into, guess what? Commutators. It turns out that commutators, I guess that's like in quantum, we didn't invent commutators. They existed for the matrix people. But quantum mechanics is called matrix mechanics, right? I think I've said that before. Okay, and then you run into one of these nested commutators. Remember this? You had a homework problem with this. I didn't make a big deal of it, but oh god, it kind of hurts my arm too. That is minus, by the way. That's not a mistake. It bothers me that those brackets are there. Oh, look at that perfect bracket. Okay. All right, minus. Then I permute the B. But then I don't permute the A on the other guy. Anyway, not that this matters. And it goes on and on forever. Okay, so that sucks. Okay, so notice what we're doing is we're just doing that. And so, now you may also recall, this whole time we've been here, I've been telling you I'm always PO'd about commutator errors. People keep saying in talks, oh, they commute, they don't commute. Or there's an error, there's a commutation error. What? What does that mean, right? Commutation means so many different things. Or it doesn't mean so many different things, but it has lots of consequences. Okay, when it comes to this method, and this is a common method, you'll hear, oh, there's a commutator error. The commutator error is that these are not zero, right? Momentum and position, p squared and v of x, p and x, p squared x. We've done this 1,000 times, right? Especially when we were doing harmonic oscillator time dependence of, the Heisenberg stuff. P and x, they don't commute. So these are not zero. So these are the commutators. Commutator error is that these are not zero. So I'm going to set this equal to each other, but these are not zero. So this method is not perfect. However, to be blunt, I have been using this for 20 years, and I have found the accuracy to be shockingly good. So this commutator error, if you set all this up right, is incredibly small. Now, notice, and here's why it's small. Notice that these are to the first power of lambda. But when you've got a commutator, you've got AB minus BA, right? That's lambda squared. Okay, but that term needs to be there, but it's not. If lambda squared is tiny, then there's no error. To make lambda small, and therefore lambda squared really small, so we needs to be small what you do is make, instead of doing, trying to jump the wave function forward in time over several nanoseconds maybe, instead break it up into units of 2 to the minus 17 seconds, remember that number? Break it up into really small segments and evolve it in time, and then do that over and over and over and over again. So we're going to repetitively evolve it in time over really tiny chunks, because lambda, which has t in it, if you make t really a delta t and make it like a million times smaller, and then do it a million times to get to the same t, your lambda is actually really small, and these commutator errors basically turn to 0. And it really works shockingly well. Okay, next thing. Now it turns out that, let's say you didn't want to do this exactly still, but anyway, but this sucks. You know, I know you're thinking like, oh, commutator of momentum squared in x, that's not hard. Potential is not necessarily x. If potential was x, just an x, that's a spring, right? That's a linear restoring force. You're going to have complicated potential surfaces, right? V of x is like a crazy function. It could be a very complicated function. So the commutators may be very complicated. Okay, so here's an alternative way to do this. This is called the Trotter something. Trotter product rule. Okay. So, all right, now what we've got from the Baker-Campbell-Hausdorff equation is that we're not going to do this in a single step. We're gonna break up time into tiny chunks and do it over and over again. In terms of the operator itself, we're going to use the Trotter the Trotter product rule, which is this. Okay. So here's the thing. Now this is perfect, and then here's Trotter's deal. In the limit of this m going to infinity of what? E to the lambda a over m, e to the lambda b over m to the mth power. Okay. So instead of doing this, which sucks, if we did this, which would be awesome, the problem is that we have an infinite number of terms. Okay. So we're not going to do that either. Therefore, let's just look at m equals 2. Okay, if you do m equals 2, all right, so I'm gonna multiply this by itself. So I'm going to take lambda a. Remember, a is an operator. I'm not putting a hat on it right now, being lazy. E to lambda b over 2. Okay, now this next part confuses me. I would normally want to put the same thing again, but I've read that this is called the symmetrized version of this problem. So this is called the symmetry. So I'm only squaring it. I'm just going to do m equals 2. And what you end up with is lambda a over 2, e to the lambda b, e to the lambda a over 2. Okay. So I'm not sure why you can flip this the way you do. I guess it doesn't matter how you write these, and so symmetrize, right, ABBA, that certainly is symmetric. I don't know why that's justified, but it makes the operation a little bit easier. So people do it this way. Okay, now I have to apply that to our Hamiltonian. And so here, let me toss that up, and let me write out how this is actually done, how this is programmed. I guess you can't really see that too well. It's just, I've been in here before, and I know I have to be really careful with the board because I can raise it higher than I can reach. I don't want to do that. Anyway, all right, now what? Let's see. Okay, so here's how this ultimately looks. Here is the wave function that has gone forward in time a little bit, and it looks like this. E to the I delta t over h bar. Of course, h bar is 1. P squared over 2m. M is 1, but whatever. again, I seriously, I always include it. I just say m is 1, and then I include it anyway. So I found that when I get confused, I need that. Did I write 2? See, 4. P squared over 2m, but half, right? A is now P squared over 2m. So lambda, of course, is minus I delta t over h bar. There you go. Minus I delta t over h bar, P squared over 4m. Operating the wave function at some present time t. Okay. And as I mentioned, what you do, now I'm going to show you how you actually do these guys on a computer. Okay, this thing. What we'll do is we'll have a wave function, we'll have 1,000 points, and we'll draw a bell, we'll draw e to the minus x squared at the center. So we'll draw a little bell function. Then you do these operators. H bar will be 1, m is 1, so it's actually kind of easy. Delta t will make it a small number like 0.01 or something like that. Again, remember that's an atomic unit, so that's, 0.01 times 2 to the minus 17 seconds, whatever. So it's a small number, and then it gets advanced that much, and then you just pull that right back over here and do it over again. You do this 10,000 times. And there you go. And then you're evolving a wave function. Now, the cool thing is, I'll show you how to visualize it too. I'll give you the MATLAB code so that you can watch, like you can put this bell curves, you can put it in a harmonic potential, and you'll watch it go back and forth and back and forth. One thing to be aware of is that this is really, it's cosine minus I sine, right? So you actually, even if your starting wave function is real, it'll have real and imaginary components as the wave function goes forward in time. Got to look out for that. Usually when I'm making movies, I plot the absolute value of the wave function, and it's just easier to look at. Anyway, I'll show you how to do all that. Okay, so now you're time evolving a wave function, but so what? Trust me, that is freaking awesome. I'm sure you'll get actually sucked into this and probably like playing with potentials and watching this thing go. It's really fascinating. All right, anyway, we got to do more. All right, so now we've got to get eigenvalues. Okay, of course I mean the energies. Right? We're doing the Hamiltonian, so how do I get the energies of the Hamiltonian? Okay, this is cool. You're going to like this. And again, I'm going to show you the code. Am I not? Okay, when it comes to actually how you do these operators, I'll talk a little bit about it in a minute, but for the most part, it's just MATLAB. I'll need to really show you how to do it in MATLAB. It's really easy. EXP minus square root minus 1, 0.01. You don't need to direct divide by 1. Anyway, it's really that easy. I'll tell a little bit more about it, but I'm mostly going to save that for, I'm going to splice in some MATLAB. Okay, eigenvalues. To do the eigenvalues, you're going to calculate this. This is a correlation function. Correlation functions are usually expressed with the letter P. Okay, so P means correlation function. Here's the correlation function. It's the wave function at time t, the overlap with the wave function at time 0. That's why I taught you Dirac notation, because I can write that stuff and you should know automatically what it means. And of course, what it means is the wave function. I'll just say that we're in X, complex conjugate. That one's important because remember, I just said the wave function will pick up an imaginary component, even if the starting wave function is real. And this is the two multiplied times each other. Integrated over space. Now, of course, at t equals 0, this is the number 1, right? Because it's just the integral of the normalized wave function squared. The integral of the normalized wave function squared is by definition 1. So this starts out at 1, but as the wave moves, it will rapidly not become 1. Okay, so this correlation function, again, it's going to start out at 1, and it will then go nuts. Okay. 1, and I think you can't be less than -1. Well, can it be -1? I think it can be -1. And I can't remember if it's -1 or if the lowest number is 0. Anyway, whatever. You'll see. All right. So what about that? Okay. Now, we have covered this. We've covered that you can think of a wave function, a state in time as being composed of a combination of eigenstates. Remember, I kept saying over and over and over again from the very first that a linear combination of all the states that are the basis of an operator, here the Hamiltonian operator, all of its wave functions, meaning ground state, first excited state, second excited state, third excited state, I can sum those up with some weighing factors to equate anything that I have, anything that my cat draws, right? So I'm going to have some weighing factor times the eigenket, where of course the Hamiltonian operator operating on that eigenket, it satisfies the eigenvalue equation. Okay. Now, this is evolving in time. So notice I left a space there. That wasn't an accident. So I'm going to have e to the minus I energy of that state over h bar, whatever t is. Okay. Now, we've covered this before, but even if you don't remember it, again, anything that I have, no matter what it looks like, even if my cat drew it, can be decomposed into a linear combination of basis functions, where those basis functions are the set of eigenkets of the Hamiltonian, of the operator in question, which is the Hamiltonian. To revolve in time, I multiply the way the state times e to the minus I h operator t over h bar, and of course because these are eigenstates, you just replace the operator with its eigenvalue, right? We've covered that a zillion times. You should be sick of that at this point. Okay, so now let's go back into here. Let's go back into here, and what does this do? This means that the correlation function, and I'll write this out again. Correlation function is now the sum of, so you got to remember, you got to make this complex times itself, so that means that we're going to have these coefficients for each, so we're going to sum over all states, ground state, excited 1, excited 2, excited 3 state. This is the weighing factor, complex conjugate times itself, so that's the absolute value squared. And then I'm going to have e to the minus I in t over h bar. And here's the thing. This guy here, without this term, right, and then this one evolving in time, because time is 0, right? So this term is 1 for this part, and then this part here is just a complex conjugate of this. So I may have, did I make a mistake here? Then this is actually positive. I may have made a mistake because if this is a bra, this is a bra, then that's positive. So yeah, I guess I made a slight mistake here. That's plus I e. Anyway, I'll double check that. I feel like I'm not sure anymore. It looks like this should be positive. Anyway. Okay, and then of course, when you have an eigenket combination, you get 1 or 0. Right, so you end up with this. What does this look like? Now, I've already explained that the correlation function itself, right, is going to look like this. And this is the mathematical form. So seriously, like when you plot it, it's going to look like this. This is the functional form. Remember, e to the I, energy times time over h bar. This is cosine plus sine. Now, you may have more than one state contributing to the initial wave function, depending on how you drew it. That's going to make more sense once you play with it. Okay, so what you can do is take the signal, which is here, and Fourier transform it. When you Fourier transform it, what it looks like is this. It's now going to be the sum of states how much that state contributes to the initial wave function, delta function E minus energy of the state, of that same state. Okay, so I know this may be a little bit like, it may have already gotten a little too confusing, but it will make more sense when we actually sit down and do it with the computer. Let me draw you what that will look like. It's actually signal analysis. You get a signal, and let's just say it's a perfect sine wave. When you do a Fourier transform of the sine wave, what you get is a single point, a spectrum with a single resonance, which is the frequency. Anyway, now what you have here is you had some initial wave function. It was correlated to itself at first, but as it evolves in time, it goes nuts. It's going to do all kinds of crazy things. Okay, when you Fourier transform that, again, it's signal analysis. What you see is how much each state contributes. The x-axis. All right, here, your x-axis is time. So when you go from time and you Fourier transform it, Fourier transformation goes from time to frequency. Well, frequency is energy for a wave. So we're going from time to energy. So the x-axis is really frequency, but we all know that that's really energy. And what we're going to see are peaks. And what you see is, this would be like the ground state. That's the ground state, that's the first excited state, that's the second excited state. And the peak heights tell you to what degree they composed what the initial state was. Now let's say that you purposely created your time evolving a wave function, and you purposely made the initial wave function the ground state. What you would see is this. You would see one peak for the ground state, because that's the only state that was present. Yada, yada, yada for the first excited state, for the second excited state. Now, of course, the thing is, you don't really know, the reason you're doing this is you don't really know what the states are, right? So when you just kind of come up with something, when you're just creating an initial wave function off the top of your head, something that's maybe like round shaped, it's not going to be perfectly the ground shape, the ground state. You are not capable, no one is capable of just thinking of what the ground state looks like as an initial wave function. You always, always, always are going to see the excited state. Sometimes you can see like a bunch of excited states, and that means that you guessed your initial wave function was a bad one. Okay. Anyway, now we're going to do this, and it's in my handout. So you'll see exactly how to get it right, how to make sure that those energies are what you think they are, right? So that they're really in units, by the way, they're units of Hartrees, right? We're going to use atomic units. So as you see these peaks and you read off the energies, those numbers are in Hartrees. So you can take that to the bank. Okay, now I mentioned, I've got a Hamiltonian. I've now got the energies of that Hamiltonian by evolving the wave function in time and calculating a correlation function. That takes one production run. Now you have to do a second to get the wave functions. The split operator method has to be run 2 times. One to get the energy via the mechanism I just showed, and the second time to calculate the wave function itself. You're going to calculate an unnormalized wave function. And how that works is this way. Now that you know what the energies are, and let's say you got the energy of the ground state, the way you calculate the wave function of the ground state looks like this. Now you're going to have, again, a trajectory of, let's say, about 10,000 steps. I'll call that tau. 10,000 steps. Each step is like 0.01 natural time units. We've covered all that. Whatever. Okay. And that's done by delta t. Anyway, okay, so now what? You got E, what you're going to do, you're going to multiply E to the I energy, and you're going to plug in an energy. So this is something you program into. H bar is still 1, but anyway. So what you're going to do is, this is a parameter that you plug into MATLAB. You're going to make it the ground state energy. So this number is here. Now I'm going to call it E prime for a reason you'll see in a minute. Okay, you're going to multiply it by the wave function over time. And you're going to integrate over time. Okay, now what this really means. Now, I'm always telling you that theoreticians have a way of making things look impossible, and it's actually really easy. What you're doing is, you're going to evolve the wave function in time by the mechanisms we just talked about. At every time step, you're going to take the wave function and multiply it by cosine e to the I t over h bar plus I sine blah, and save that. And then you're going to add that to the same thing calculated at the next time step. And add that to the same thing calculated at the next time step. A sum where you're always adding in the elements of the numbers of the sum is an integral. So let me, integral equals 0. For I equals 1 to 1,000, integral is equal to integral plus expression, end. That is an integral. Hopefully you can follow what I just said. Int is equal to 0, for I equals 1 to 1,000, int is equal to int plus whatever. The whatever is what you're integrating, int is, once the loop is run, that's the integral. That's what you're doing here. You're going to take the wave function, you're going to time evolve it, multiply that times that, and then you're going to add that to the previous result. Anyway, you're going to do that in a loop. The loop over time steps in the simulation. Again, if this isn't making sense, it will when we sit down and actually do it. Okay, so on. What is this equal to? Now remember that the wave function is actually a sum of eigenstates that are evolving with a coefficient times e to the I energy of the eigenstate. Okay, so let me rewrite that. Let me give myself some room. This is going to take a little bit of space here. Okay, so there's that. Then I've got the sum over eigenstates, n equals 1 is the ground state, and so forth and so on. Here is the weighing factor for the initial state, as it is represented by the eigenstates. Here, now the time evolving state is now a ket, so I've got the time evolution operator is minus I Hamiltonian. Okay, energy of whatever state I'm talking about. And then times, I guess I need to use, I'll use Dirac notation here, but really, let me just remind you that, but let's make it a real wave function, the a to the n wave function. And let's just say it's the ground state, right? Sorry, it's a sum. N equals 1 is the ground state, n equals 2 is the first excited state, on and on and on. Okay, so what does this equal? Okay, this ends up being really simple. It ends up being, here, damn it, I'm not using the thing very well. Let me continue on down. Actually, almost done, so we have time to do some computer work. I think I messed up the last lecture and talked way too long. Anyway, oh damn it. Okay, so how does that evaluate? I'm almost done. Almost done. Let's see. I'm not going to find my spot in my head. Okay, so that is equal to the integral of the sum of states, and like a lot of things, this is going to simplify. Okay, and here we go. Side, whatever state we're talking about, ground state or excited state. Okay. All right, so what? Okay, now here's what's happening. You're creating an interference. We have constructive and destructive interference right here. Right. This is this is cosine plus sine. If E prime is not equal to any particular a to the n, you get destructive interference, right? You're just adding in sine, you're just adding in sine and cosine. And it's up, it's down, it's up and it's down. As you integrate, think about how you integrate cosine. The integral is up, then it's down, and then it's up, and then it's down, and then it's up, and then it's down. It's just oscillating about 0. So if the number you plug in for energy is not equal to a particular energy of a state, it's going to just, this thing oscillates about 0. It doesn't go anywhere. Okay, but if you parameterize it, which is your E prime, if you set that equal to, let's use the ground state, then that term is 1. And you see what you're doing is that every time step, as you do that integration, I just described that out, in words. I know that's weird, but anyway, I described that in words. What you're doing is you're adding on to this integrated thing. You're only adding into it the ground state. Because all the other states, they add in, they add out. They add in, they add out. In and out. But if E prime is the ground state energy or whatever energy, it always adds in. Because this doesn't oscillate. E to the 0 is 1. That doesn't oscillate. So, as you propagate the wave function in time, the component, and you multiply it by e to the I energy, where you know the energy, let's say it's the ground state energy, as you add in the propagating wave function times this factor, only the ground state is being added in repetitively, whereas the other states are being added in and then subtracted out, and added in and subtracted out, and added in and subtracted out. They don't get anywhere, but the ground state is always being added in. Now, eventually, it doesn't take too long until the state looks exactly like the ground state, and all the excited states are just basically washed out. Now, you could set this energy for an excited state too, and then the same thing would happen. So anyway, and we'll see that in practice. Okay, so and let me write down an algorithm. I'm concerned that, again, while we'll do it, I want you to just see how really easy this is. So what you're going to have is a wave function, let's call it psi. And you've got that evolving in time with the split operator method. So you have the simulation is being run 10,000 times. And you're evolving the wave function, so you won't see that. What you've got is I1 is just, the wave function is a 1,000-point column vector, right? I1 is a column vector of 1,000 points, it's all 0. But it's integrated, and by integrating, I1 is equal to I1 plus exp. Now, you've already told it that I is the square root of -1. MATLAB knows how to deal with that. Okay, you have told it what energy is. You defined delta t. Multiply that by t, which is just, advances it in steps. And then divide by h bar, which is just 1. Times the current wave function. Okay. Seriously, it's that easy. And then at the end of the simulation, after 10,000 steps, I1 is the ground state wave function. Okay, and it's the ground state wave function. It's not normalized because this is kind of nuts. You can normalize it after the fact, but anyway, it will be whatever state corresponds to that energy. And again, we'll say it's the ground state. Okay, last bit is to cover how do you do the operator. So I mentioned that the potential operator, e to the minus I, potential energy, t, delta t, that's seriously easy. You'll see that in an example. And you're going to take the wave function, a bell-shaped wave function that you'll just just think of whatever that might look like and just create it. You've created bell-shaped wave functions before, I think. That's easy. The momentum is not so easy. So recall that a Fourier transform His die, I know, looks like this. It's infinity integral. Remember, we covered this on the first day. And I wanted you to see that because I knew I would be covering this today. Okay. E to the minus 2 pi I xp dx. Okay, and this is the wave function in P. And I didn't put the normalization, whatever, I don't care that much, it's not that big a deal. Okay, now what this does is, the reason that this is actually kind of a biz knocker is because this integral can take a little bit of time to evaluate, and you only get the wave function in P at 1p. So let's say that your wave function in x is like 1,000 points long. So, right, we're going to simulate a 1 nanometer box, and we're going to have steps of 1 over 1,000 nanometers. So the wave function is a 1,000 nanometer column vector. P will also be a 1,000 element column vector. So every one of those elements has to be calculated with an integral, with P being defined, and then you integrate it, and then you get that single element of the column. And then you have to do that 1,000 more times. This gets time consumptive in a big way. One of the biggest advances in mathematics was the fast Fourier transform, where instead of a sum of 1,000 integrals, it's actually just a single integral. It is a very, very complicated math trick. You actually have to do it in assembly language. It's really nuts. Anyway, it makes these very quick. But now you need to know how they work. So a fast Fourier transform is not a Fourier transform. It's really a discrete. It's a discrete Fourier transform. And the differences are pretty important. So you need to know how that works. Okay, here's how it goes. Let's take a data set. Point 1, point 2, point 3, point 4, point 5. Okay, and I'll draw something that looks like it's really a point, but anyways, let's just say it's a bell curve. Okay, now what I'm going to do is I'm going to Fourier transform this, fast Fourier transform, FFT in MATLAB, and then I'm going to plot it. And as you can imagine, I've already done that. Now, it is a basic theorem in mathematics that if I start with 5 points, I need to end with 5 points. You can't create information. Okay, let me just show you how it looks. It looks like this. Okay, but how do you interpret that, right? Now, here's the thing. Remember I said that this is going to be a 1 nanometer simulation. This is a particle in the box. The box is 1 nanometer wide, right? 5 points within that nanometer. That means my delta x is 1/5 of a nanometer. I say 1 meter, 1 nanometer. Okay. Now, when you Fourier transform this, you're going to be you're starting out in real space, and you know the Fourier transform of real space is in momentum. So, what are how do you interpret this part? We'll worry about that in a minute. But what is the x-axis? Because you see, when you multiply momentum, the momentum operator times this wave function is actually the wave function value times its own x-axis. So you see what's happening here is if I'm going to do momentum on the momentum wave function, and this is the momentum wave function, this is the real space wave function, and you know that the Fourier transform is the momentum space wave function. So to operate on momentum with the momentum operator on the momentum wave function is what? I don't have a formula for it. What it is the value of the wave function times its own x-axis. Because this x-axis, this was an x, this is x. But this is p. So p times the wave function is just the x-axis value times the wave function. But now you got to know what exactly are the values, right? Because they, this is really 0.2, 0.4, 0.6, 0.8, 1.0 nanometers. So you know that these are in some units of kilogram meters per second, right? I'm doing the SI. Anyway, but what are they? Okay, here's how this works. Each point is this. It is 2 pi over L. L is 1 nanometer. So you can see how it's easy to translate. This is 2 nanometers, 2 pi over 2 nanometers, times, let's call it n, where this is n, where n points to first point, second point. Anyway, n goes as 0, 1, 2, I'll be specific to this example. 0, 1, 2, 3, 4. 1, 2, 3, 4, 5 points, right? I started out with 5 points, I ended 5 points. So the new axis is 0, 2 pi over L, 4 pi over L. See? Now you know what the x-axis is in momentum space. So if you're going to evaluate momentum operator times the wave function in momentum, or better yet, exp minus momentum squared times the operator, it's just that's 0, that's 2 pi over L, exp minus that number squared times that value of the wave function. And that's, you remember the split operator, minus I p squared over 4m times delta t over h bar is 1. Anyway, I just want to get across that this is how the split operator works. Wave function in space for your transform, but it's crucial to know what the x-axis is. Okay, that isn't quite totally correct though, because here's how it really works. I wanted to just ease you into this and make it easy. However, MATLAB has a weird thing that it does. N is 0, 1, 2, minus 2, minus 1. That's how to actually read this. It's weird, okay? It goes forward and then it goes backward in a forward sense. Anyway, to the middle and then to the other end going back. You see what I mean? Again, 0, 1, 2, but now let's start at the other end, but go forward, minus 2, 1. Anyway. Now imagine if it was 1,000 data points, 0, 1, 2, to 599, forward, 0 to 500, minus 499, minus 498, minus 497, minus 496, to minus 1. The last element would be minus 1, 2 pi over L. The first element is always 0. Right? That's called the DC contribution. Anyway, you need to know that that's how MATLAB, that's how it indexes the Fourier transform. MATLAB does it in a very strange way. But when you Fourier transform this, and then you do the momentum operator, it's really easy, but you've got to make sure you know what the point's x-axis actually is. Now, I just showed you how to do it, just don't mess it up, right? Once you know the x-axis and the point, then you can do the split operator. It bothers me I'm not doing this right. exp, what is it, minus I. MATLAB, you can tell MATLAB I is the square root of minus 1. And it will understand what that means. It will actually turn this to cosine minus I sine times p squared times delta t over 4. Sorry folks, the camera just crapped out. I just wanted to write that operator correctly. Again, the way you do the momentum split operator, the momentum part, exp minus I, and you can tell MATLAB I is the square root of -1, it will understand, times p squared. Okay, again, that is the point in the x-axis, which you now know how to figure it out, squared times delta t, over 4 over m over h bar is 1, times the wave function. That times the Fourier transform of the wave function. So it really, you actually do this as a sum from what, like in my example, there's 1,000 data points. It's the wave function is 1,000 points long. So this, you just do this for every point, knowing what the p-value is, and of course knowing what the wave function's value is from points 1 to 1,000, after having been Fourier transformed from real space. Then you Fourier transform it back to from real space to momentum space. You do this operator, you go back to real space, and then you multiply the real space wave function times the same thing, except that instead of p squared over 2m, it's just the potential energy. Okay, anyway, gone on too long. Let's do some computer work, and you'll see how this really works. And again, I have a module, I have a PDF that explains this in enormous detail, and you can figure it out from there. This will be the basis of your final. You'll figure it out. Okay, I will see you all in a week.